Um, okay, thanks for inviting me here. And I'm going to talk about shock treatment using C equal to 1 techniques. I thought that's what I would call my, give my title as, but treatment of shock waves, in one-dimensional hydrodynamics using and developing on some work that was started during the days of C equal to 1 matrix model on one-dimensional free Fermi gas. It appears that they have experimental realizations in ultra-cold atom systems, much of which I learned from Manas here. So this is based on ongoing work with Manas Kulkarni and Takeshi Morita. So there was some other work on one-dimensional Fermi gas by Takeshi, which also played in this. So let me start. So this is what we will do. So that's the goal. So we'll consider unitary non-equilibrium evolution of an one-dimensional gas of fermions. And so there is a particular limit called Tonks limit of a Bose gas in one dimensions, which is defined by an infinite strength delta function repulsion. So there is a particular way of taking this infinite strength limit, that's called a Tonks limit. And much of the analysis for the Bose gas in that limit will also go through for the Fermi gas. Now, as I said, this kind of situation, time dependent as well as equilibrium situation, is experimentally observable these days in ultra cold atom systems. I can share some literature later on with people. Some of them have appeared in Nature, Science, etc. So both the fact that it's experimentally observable and the fact that there's a lot of work going on for the last several decades, makes this thing interesting. So we'll consider. So we are interested basically in time development of these. The initial non-stationary state can be developed by quantum quench, which is a favorite method for experimentalists, because you can dial some parameter in the Hamiltonian and quickly change it. So that's called a quantum quench. So one in this context, this has been used in 2012 and in subsequent work as well. So you have a one-dimensional gas. I think in this particular experiment they took Bose atoms, but with hard repulsion, and they were kept in some parabolic trap to begin with, and the trap was switched off, and final confining potential was that of a periodic box. So it was a circle. So from a parabolic trap to a circle, and many experiments were done with them. Okay, so we will consider a production of two aspects of thermal evolution and do analytic calculations. One is the production of shock waves. That will be the main emphasis of this talk, and also I'll make some remarks about thermalization. Both of these have interesting non-trivial features. So let me discuss shock waves first. Now, analytic treatment using conventional hydrodynamics does not describe shock waves because the density function, the fermion density, develops singularities. And density, of course, is one of the basic variables. So if it develops singularity, for example, the derivative blows up, spatial derivative blows up. So the conventional equations can't handle it. So how have people been trying to attack this problem? So by addition of various terms, all of them are justified by using various reasonings. I'll give you an example of that kind of a term, which compare well with the numerical n-body quantum evolution up to the formation of the shock, but it fails beyond. Okay. So we will show by generalizing earlier work in C equal to 1 matrix model, which I'll review a bit, that conventional hydrodynamics in this regime of validity, first of all, can be derived from the description of fluid droplets in phase space, which appeared in these works, and generalizing on that. And the fact that the droplet dynamics remains valid beyond the formation of any number of shock fronts, we'll give some examples, which appear in phase space as folds or overhangs. But the point is that the folds do not have any sharp kinks or anything like that. The folds are smooth. Okay, the fact that the folds are smooth makes it possible to handle time evolution through the formation of shock fronts. And so this is like an example of desingularization, okay, of a singularity by going to one higher dimension. So namely from real space to phase space. Okay, and I'll give you examples of these things. Our treatment does not need ad hoc terms. The phase space evolution equations are derived from a second quantized fermion theory in a classical limit. It's a large n limit, where n is the number of fermions, using the method of quadrant orbits. I'm not going to explain this. So, sorry.
It's a little similar to the previous one, right? In that, is it correct that these ad hoc terms basically correspond to a guess for UV physics? And
they do try to, sort of weaken the effect of derivative terms. So in that sense, it is in a way. So it's just an additional control on the derivative terms. That's what they try to do. Okay, and the arguments from one paper to another, they differ a bit. So I'm not going to summarize what, but it is indeed true. It's try to give some rigidity to the thing, so that the derivatives don't.
What plays the role of dimensionful parameter when you go from one low dimensional to high dimensional? Is it just the volume of the phase space?
There is some dimensional full parameter that in our work.
No, when you introduce this ad hoc.
Yeah, when they introduce the ad hoc terms. Yeah, indeed, there is a dimension full term. You mean what is the logic of no idea? So I'm not going to describe this too much, because first of all, I don't know much about them. It's called a quantum pressure term. I'll show you what it looks like. But this the thing is true that it's tries to dampen. Yes, hi Manas. Yeah, please tell me.
The ad hoc addition.
Yes.
Sort of, it's like you just add a term to some sort of effective Landau-Ginzburg theory, and that at least produces the right nonlinear term you would expect for free fermions. The right nonlinear term you would expect for free fermions is rho cube. So what kind of term I can add in the Landau-Ginzburg theory that produces this ad hoc term? But in doing so, it wrongly, there are other terms in the Landau-Ginzburg theory, but that are not really there in the field theory description. So that's one comment, yeah.
Right. So, yeah. So I'm just going to give you an example of that term without justifying it too much, because it doesn't work anyway. So, okay. Right. Okay, so conventional hydrodynamics, in the case of this one-dimensional fluids, it looks like this. I think okay, so anyway, this is continuity equation, and this is analogous to Euler equation, okay, which is basically applying Newton's law to fluids, and yeah, I think I have a slide later on in which I derive this, okay, from the phase space description. So anyway, this is easy to understand, and clearly these equations involve derivatives of the density, and these equations fail when the density develops a singularity, and this will be my definition of a shock. So that is to say that in the course of time development, this fluid at some time Tc and at some point xc develops singularity, okay? So we'll call this a shock wave, and this xc will be called a shock front. And so this is one of these terms that we're talking about, and this is what. So this was suggested in the context of capital V. I should say what it is. So this is a trap. This is a trap potential. So this is a Fermi gas, okay, in which there is no interparticle interaction, but all of them are in some external potential, that's capital V. And so rho xt is the fermion density, and rho v, and rho v is the fermion momentum density, okay? So rho times v, and v is sometimes called a specific momentum density, okay? So rho v is the momentum density, and this is the number density, rho xt. And the Euler equations look like this. So this, the first equation. Oh, okay. So it's sort of. Sorry. No. So yeah, this is for non-viscous. It's one dimension. Yeah. You mean here?
Yes.
Well, if you just try to evolve these equations using this, so you will see that whenever you hit this derivatives, you do have a problem.
But is that problem because of the nonlinear rows? Because you have to take a product of delta functions, and that product of delta functions is not well defined. When you take rho squared.
The rho del x rho, you mean?
Yes, because rho.
Rho remains.
I see.
Rho remains finite. It's only the derivative of rho which is infinite.
I see. So you're saying it's not a
Development has a problem when you have basically. Yeah.
When the derivative of rho, it doesn't necessarily have a delta function like singularity. It might be just like 1 over x minus x.
It has a kink. It has a. I'll show you the picture. Maybe the picture is there in the next. Yeah. So let me show you how this shock formation business happens. So you start with some fluid profile. So let me draw. So let us say that you have some box, and so I'm drawing the phase space of some Fermi gas in a box. Okay, so this is x equal to minus L, let's say, and this is x equal to L, and the Fermi fluid is here. This is your upper Fermi surface, P equal to PF, and this is your lower Fermi surface, minus PF. And this evolution is done with the condition that the fluid, okay, has both top. It's symmetric. So this one moves that way, and this one moves this way. Okay. And so then, and what happens to the density as a result? So the fermion density, so if you put a wiggle like this, okay, what does it mean? that means that, you know, this height from here to here, okay, measures for you how many fermions are there in this delta x interval, okay? And this moves this way and that moves that way. So you have a left moving and a right moving peak like this. This is all in densities, okay? And eventually what happens is that, as you can see from this example, that the higher fellows, okay, correspond to higher momenta, okay, because they are at that higher height. It's simply the fact that these guys have higher momenta, so they move faster. So after a point, you know, these guys take over these fellows, and it just picks up, you know, shock. So the higher compression regions move faster, so they pick up a shock, and that's what happens here. So this is what the numerical evolution gives. This is from the paper of Damsky in 2006, and with their modified hydrodynamics equation, they can, sorry, so I should say which one is which. So the dashed line is the exact n-body, is a numerical n-body simulation, and you know, that shows you this sort of sharp peak here, and some, and this is at some, so these are different time snapshots. So this is an early time snapshot, and then it sort of moves, the two peaks move, and you have a shock formation here as well as here. Okay, and so there are some time units that are used here. So at t equal to 82 in their calculation, the shock is formed. Okay, so t equal to 82, and sorry, this should be xc, and at a value of x equal to 118, you have a shock here. Okay, and as you can see that the solid lines which correspond to this mean field equation with that term which they call the quantum pressure term. So this stuff. Yeah.
So what are these n bodies? What are the particles? And what is the interaction?
There is no interparticle interaction.
There is no?
No.
It's free particles.
Three particles. Three particles done with some.
Hardcore potential.
No, these are the fermions. These are fermions. But the same analysis holds for bosons in the Tonks limit, in the infinite hard sphere repulsion limit. So what is done here is to take the Slater determinant of n fermions, okay, and simply evolve them in time. Okay, so you start with the Slater determinant of fermions, which are all eigenstates of the old Hamiltonian. Okay. And now you have quenched it, you have a new Hamiltonian now, so that the same Slater determinant now is not stationary state, so it evolves. And what they have done is to take the density, and the density is being plotted. Density is a function of x and t, so either you can do a plot or you can do this. So different. So this is rho as a function of x, so I should say. This is x, and this is rho as a function of x at various time snapshots. Okay, and the point that I want to emphasize here is that beyond the shock formation, you know, the mean field equation, even with that high derivative term, okay, shows some sort of you know, oscillations which are clearly spurious, because the exact calculation does not show that. And we will.
But the exact calculation wasn't done with extra term, right?
Exact calculation was done? No. There is no extra term. This is a Fermi gas. We know what the quantum system is. That was Spencer's question. We know what the quantum system is. We are trying to develop some analytic method for, you know, doing things. So to these people, the analytic method that was available was conventional hydrodynamics. That didn't work. So you add additional terms, okay? And that's working till the point of the shock formation, okay, but not beyond. Okay, so you have spurious oscillations in this. Okay, yeah.
When you say the similarity is no worse than caustic if you have light-phase.
It is like that. I believe, yes.
Here the similarity is really spurious. It's the way you treat the phase-space body.
Projection from phase space to configuration space is what is generating the spurious signal.
That's correct. That's what his remark was.
And your fundamental description doesn't need to know about that singularity.
That's right. That is absolutely correct. In fact, it's a little, yeah. So the difference with caustic formation is that here there is a coordinate dependence also. You know, instead of x and p, if you use some other description of phase space, then the shock formation might not happen for specific time evolutions, or it might happen at some other time, etc., etc. So the phase space description is fundamental. There, you know, you can. So let's go. Yeah, that indeed, that's the point. Okay, so let's just say just one slide about C equal to 1 matrix model. So it was the matrix quantum mechanics with
Putting these orders together is really very misleading.
What?
They did very different things.
No. This is only no. So this is the reference to this point. This is proposed to be a non-perturbative formulation of quantum string theory in 2 dimensions. So this is the reference for that, and the main reference for what we are going to talk about today is this one. Okay, it's a work with Spenta and Avinash, and
I didn't mean to imply anything.
No. So that
The main conflict is what these people did.
yeah.
Somebody did wrong and somebody did right.
Yes, sir. I'll mention that. So conventional hydrodynamics is similar to the collective field formulation of C equal to 1 matrix model, which was done by Jevicki and based on the work of Jevicki and Sakita. And some of the limitations of that work was already known, and we found that indeed it is true that it is only under some approximation that the collective field formulation works, much the same as the approximations needed for conventional hydrodynamics. In particular, okay, if there's a phase space fold formation that happens, then you have to use a fermionic formulation, which allows you to go to phase space, and not the collective field formulation, which gives rise to conventional hydrodynamics. Okay, so for our purposes, we'll need the fermionic formulation of the matrix quantum mechanics, and that's all I have to say about C equal to. I'm not going to use matrices anymore. So the eigenvalues of so this is the matrix quantum mechanics. So there's a matrix M of T. And the eigenvalues, there are n eigenvalues of that. Those guys at any time t, these are the eigenvalues, and they behave like fermions, which are subjected to a one-body Hamiltonian. So there is no mutual interaction between these fermions. These fermions are free, okay? And the Hamiltonian is just a kinetic term plus this is non-relativistic. Kinetic term plus potential, and how am I doing it? 6 minutes, Jesus. Okay, all right. So I'll go. For the C equal to 1 model, this was, but we'll take this to be general. Okay, all right. So this is an important issue, is that a large n limit of the fermionic model, you can do it very carefully, start from the fermionic path integral, and show that the fermionic path integral even exactly can be described in terms of rather than the coordinate space variables, it can be described in terms of the Wigner phase space distribution, and the description from the fermionic path integral to a path integral in terms of the phase space density can be rigorously done, and in the large n limit, the phase space density becomes a classical variable. This is a Moyle product that in the large n limit becomes, so this is exact, okay, and in the large n limit it just becomes single normal product, so u square is equal to u, okay, which means that you can have values 0 or 1, Okay, that gives you the droplet picture. Okay, U equal to 0 where there are no fermions, and U equal to 1 where there are fermions. And of course, in the semi-classical limit, you can think of sort of phase space as being built out of small squares, each of size h bar, and they can only have 1 or 0. So that's the thing. And there's a fermion number conservation stuff, and this is the really the Newton's law in phase space. This is the Euler equation in phase space. Okay. So as I said, this U square equal to U gives rise to droplets. And so this is a particularly simple kind of droplets, which we call quadratic droplets, where the property of this droplet is such that, so this is the region where there are fermions in phase space. This is a picture of phase space. Okay, that any vertical line crosses this Fermi fluid droplet in two places, P minus and P plus. Okay. In this case, so let me just say this, then the fermion density looks like this. This is just says that it's a quadratic droplet, and as I explained in that figure, that the density is just given by P plus minus P minus, right? Because that's the integral of U, okay, from here to here. Okay, so that gives you the, similarly, you can, so that's counting numbers. Similarly, you can count momenta, okay, and you can count energy. Okay, therefore, that gives you a description of rho and V in terms of these two fluid profile quantities, P plus and P minus, like so. Okay, and it also gives you the Hamiltonian. Okay, the Hamiltonian is just counting the various, and in each phase space cell, you just find out what the value of HXP is and keep, just multiply that. So then you get a Hamiltonian. You got a Hamiltonian, and these are your variables of hydrodynamics, rho and V. You can go back and forth from rho and V to P plus and P minus, etc. Okay, so the equation coming from the phase space Euler equation is an independent equation for P plus and P minus. Okay, that's what it is. And now we substitute for P plus and P minus the values that you get for rho and V, and you get these equations, the conventional hydrodynamics equation. As you saw, this has been derived under the assumption of quadratic droplets. Okay, but you can have more complicated things such as this. Okay, in which there are 4 places in this example: P1, P2, P3, P4. Okay, so what happens as a result? Okay, forget this slide. You have like big fluid, some here and some here. Okay, this is infinitely far away, so it's like that there is an independent conventional hydrodynamics happening here and here. Okay, so the densities do split like that. Okay, rho 1, 2 and rho 3, 4. But the velocity field is complicated. Velocity field is complicated. Okay, as a result of this, and it is again true that the phase space Euler equation gives you some local equation for each segment of the boundary, fluid boundary. Okay, but combining these and applying this, you can easily see that the conventional hydrodynamics equation fails. It doesn't work. Okay, so if you use this equations for rho and V and use this dynamics, then conventional hydrodynamics does not work. So what do we do then? We use a fluid particle description. That is to say, we say, well, so first of all, the dynamics is happening near the boundary. 49 seconds. I would need probably 3 minutes, 4 minutes. Okay, so what we do is the following. We'll say that let us focus on a particular particle, okay, fermion, here. And we'll simply track the evolution of this. Okay, so that we will call P of, so the given Fermi fluid could be this, okay, and we parameterize fluid boundary by some parameter S. Okay, so this point to begin with we would call XS and PS. Okay, and then we time evolve by taking this S and P to be the initial position for a particle mechanics, and I know the Hamiltonian, so therefore I know what happens to this guy. So this fellow goes somewhere here in phase space, and we track all the particles. Okay, so that gives us a new fluid boundary. So this description does not have any problem at all. Now, however, these equations x equal to xst and p equal to pst at any given time, freeze t now, at any given time t, if you want to eliminate s and find a function p of x, that might give you problems. Okay. Why? Because suppose it is so that x is a monotonic function of s, then there is no problem. You can invert it. Okay, so you can invert this, forget about t, I have frozen t here. You can invert this. S is a function of x. Now put it in here, you will get p as a function of x. No big deal. Okay, but if del x del s equal to 0, if there are x turning points, okay, then you can't do this inversion. This will be multi-valued, and that will give you multi-valued functions of p. P as a function of x will be multi-valued. So that's the fold. That's the appearance of folds and overhangs and so on. So this is the thing, that there are all these cases, S1, S2, S3, S4, blah blah, where these things happen. You have multiple valued because there are x turning points that have happened here and here and here. Okay, so there are x turning points. Okay, so this is a particular our algorithm for finding out where at what times such x turning points start appearing, and here is our first plot. So let me explain this. Okay, look at the red curves. Okay, so the red curves are, so this is for a particular, this is for a free fermion thing. Not, there is no trap. There is no external potential, and the red curve is the phase space droplet. This red curve. Okay, this is actual evolution. So to begin with, actually this is a red and a blue. Okay, so imagine that this is red. Okay, red and blue actually have coincided here. So so this is red. Okay, and I'll talk about the blue also later on. So this red curve, this is the beginning profile, a segment. I'm just showing a segment of the phase space droplet. Okay, and I have taken p minus to be 0. Okay, so the lower down part of the fluid is at 0, and this is some blip that has been added to the upper part. Okay, and as I said, it would develop an overhang, so it has developed an overhang, this red one. Blue guy is a density. Okay, so when p minus is 0, rho itself is p plus, because it's p plus minus p minus. So it evolves, it shows a sharp thing, but you can keep plotting it, okay, because we know how rho is constructed. Rho is constructed out of bits. Okay, it's between these two things and these two things. You just simply subtract this out, and you have a nice picture. Okay, so this we can do. So here is a picture of the same initial condition that Damsky had used. Okay, and so here we find, in another way of doing it, that there is an exact agreement with the numerical calculation. Okay, and there's no problem. Using the phase hydrodynamics, we describe the exact n-body simulation thing, and these are the these are the various moments, okay, of these, since I have no time at all, I'll just show here that this shows thermalization, and the way this thermalization happens is completely different from, so there are two kinds of ways I can say it in some discussion session or something else, okay. One is that the box size is very big, okay, and the thermalization happens in a local region, it's called subsystem thermalization, and before anything like a reflection happens, and reflection is a problem for that kind of approach to thermalization. Here is the other way around, there's a box, the fermions keep hitting each other, and it is the multiple reflection in the limit of a large number of reflections it thermalizes, okay. That's a different thing, so that's the kind of stuff that we find here. Okay, so this is the last figure in which we show, I think it's the last figure, we show that, you know, we can handle no folds to one fold to two folds and back to one fold, etc., etc. So, so we can just do this. Thank you. Yeah.
So, okay, great talk. The way you resolve this hydrodynamic singularity is because you knew the underlying microscopic theory. That's the theory of free fermions.
Yes.
Now, let me go back to this question which Samuel asked. Suppose I am not working with, see, it's because you have free fermions that you could say that the particle which is more energetic was moving faster and a fold develops.
Right.
Suppose I take shocks, you know, which are in interacting systems. Do you expect a mechanism to be similar? I mean, because this is a coordinate singularity in some sense.
Yeah, we have started thinking about this. I wouldn't stick my neck out. I don't know whether this mechanism will work or not. Yeah, for weak enough interactions, it will, of course, as one expects. But in strong interaction, I don't know what happens. So in fact, maybe an interesting thing here is that people tried to do this for Bose gas. Okay, they found that there were all kinds of problems. In particular, they didn't understand thermalization. Okay, but somebody suggested, I forget the name, Manas, do you remember who suggested this for Bose gas? That think about the infinitely strong repulsion. Okay, probably. So then they found that problem could be solved. So there is an example of an infinitely strongly interacting bosons, okay, which can be solved, and in our method also it can, but that's because it's the dual formulation in terms of free fermions. So this could be just one fortunate circumstance, but in general, for more complicated stuff, like for example, you might say, does this kind of thing happen? Yeah, I don't know really. Yeah.
I mean, in general, low-dimensional interacting systems.
Yes.
Usually, you end up getting these effective higher derivative terms in the effective description, and usually such systems have these dispersive shock waves. So, but the exact derivation is usually very hard. But there are models in which you can get these higher derivative terms reasonably exactly.
Yeah. Yeah, that's right. I mean, they use nonlinear Schrödinger equation as the starting point, and but then the approximations just go completely haywire. So, hi Rajesh. Yeah.
So the normalization, do we expect that it will become one of these generalized bits ensemble?
Yes. Yes. Yeah. I forgot to. This kind of behavior that I showed, that Takeshi and I had worked out, and indeed that's what we found there. That it becomes GGE. Yes.
So the second question, this thing is confusion related to this coordinate singularity business. While I understand in phase space it is smooth and the same, but when you actually measure the density, that is a physically measurable this thing, right? So when you say that you can choose a different coordinate and remove this, what does that really mean? I mean,
So,
some preferred set.
No. That's just a theoretician's kind of remark. You are absolutely right. Rho of x, of course, is a measurable thing. It means something that x. But I'm saying that if you really wanted to describe, so the history of this is the following. So there's a Fermi fluid. Okay, it's developing some singularities. Is there any way at all in one lower dimensional? Is there any one lower dimensional description? Okay. In which I choose a different polarization of phase space. Okay, instead of xp, I use theta and r. Okay, that's right. That's so. If it is like this, so Avinash might remember somebody in ICTP was doing this. Is it McLaughlin? So you have some stuff like this, whatever. So clearly they would, they would tilt, etc. But show that there is this theta r description in which no multi-valuedness appeared, but in terms of x it did. But yeah, you are right. I mean, when I am measuring something, that's of course x has a meaning. Yeah. Yes.
That's what you're really interested in. That's the geometric object, but it looks complicated when you project in certain directions.
Right. Yeah, so I would like to understand a little more about the general story. Yeah.
So we'll go on to the next.